Hello, everyone, and welcome into your week 3 review video. So, we are well into week 4 at this point, but we had the exam last week and no quiz. So, I wanted to go over some of the problems that caused issue on the exam. Now, the good news is the exam is behind us, so we can just look forward to new and better things, greener pastures ahead. Also, I believe we only have 4 more weeks left. So we are almost after this week. So we are almost halfway through with the class. So this exam covered most of the beginning stuff we talked about. And then specifically it ended with the derivative, which is chapter 4. So the questions that we're going to talk about today are from sections 2.4, 3.1, 3.2, 3.3, I believe 3.4, and 4.1. Now again, I'm going to timestamp this video so that those who are watching can click to see any problem they want without having to watch the whole thing or guess what it is. I'm hoping that's working out fine. If it's not, just send me an email. Again, office hours are by appointment, so please come see me for those. I still haven't seen anybody for that. That's fine if you know if you feel comfortable with material. By all means, don't come to office hours. But if you don't, please use them. This is an online course, so you really have to use all of the resources that that are available to you, and that's one of them. All right, let's get started. So section 2.4.37, section 2.4 problem 37. So this had to do with, this is the section I think on interest. It was, we were talking about exponential functions and logarithmic functions here. So the question says, find the interest earned on $10,000 invested for 5 years at 4% interest compounded as follows. A, annually. B, semi-annually. So that's 2 times per year. C, quarterly. So 4 times per year. D, monthly. And E, continuously. Well, there are formulas for these. So as long as you know the formulas, and then there's one for this. It's really just knowing the formulas and knowing what to plug in. So when we have interest that's compounded not continuously, so just general compound interest, we have a formula. And that's A, that's amount, equals P times 1 plus R over M to the T times M power. And here, let's actually move this up. I can write what all of these letters mean. So this is amount. This is principal. That's what you start with. This is the time in years. P is the time in years. And then M is the number of times per year. And finally, R is the rate. So let's highlight these. T is the time in years. I'll give that yellow. R is the rate. Here's our number of times per year. We have another color. Let's try this one maybe. P is principal. Okay, so we have this little color-coded formula. Um, so all we really need to know how to do this problem is to know what number to put where, and then how to put it into a calculator, because this is not really something you can solve kind of on your own. I mean, you could do this math, but it would be very, well, maybe. Either way, it would be difficult. So there is one more formula, and that's for continuous compound interest. And this is A equals PE to the RT. Some people like to remember PERT. I don't know if that helps you or not. It looks like PERT. I don't know. I think everybody has a preference of their own for that sort of thing. So this is E, as in the number E, to the power of the rate times the time, and then the principal is out front again. So that's just a different formula. So now we're just going to plug these in. So here for A, I have, so A equals 10,000 as the principal, and then 1. So let's actually write everything up over here. So I have the principal. It's $10,000. This is a good thing to do whenever you have kind of anything that involves like a word problem or just any of these interest problems. So time in years, that's 5 right here. Rate is 0.04 because that's how we write 4%. Okay, back to it. So we know that in all of these problems, we're going to have the principal's going to stay the same, the rate's going to stay the same, and the time will always be the same. So what I'm going to do then, just for making this, just to make this a little easier, I'm just going to copy this stuff. Since we know those will all be the same, I'll change the letter. Okay, so the rate, the time, and the principal are the same for each of these letters, but now the only thing that changes is M, right? That's the number of times we compound per year. So when we do it annually, we only compound once per year. Semi-annually, it's twice per year. Quarterly is 4 times per year. And then monthly is 12 times per year. Now for E, we have the PERT. So 10,000 times E to the rate times time. All right. So now the rest is just a matter of plugging these into your calculator. So what I get is 12,166.53. Remember that we round up. 12,189.94. 12,201.9. 12,214.03. Oh, I skipped one. This is actually there. Okay, and this is 12,209.97. Okay, these are all dollars. It's important to remember our units. Now, one last thing. None of these are remember the question asked for interest. Find the interest earned. Now, what I've given is the total amount we're left with. So in order to get the interest back, we have to subtract the principal. So we figure out, how we figure out how much interest we've earned as we see where we're at now, subtract what we started with, and the difference is what we gained over that time. So I'm not going to do the math because it's pretty straightforward. but I'll circle this. So to get the interest, we subtract the principal, which is $10,000, from each number. So we can think like this. And then, of course, you'll get $2,166.53, $2,189.94, $2,201.9, $2,209.97, and $2,214.03. We're basically just taking the one off the front. Okay, let's move on to the next one. So these next two questions, so all of these or something similar should have been on your exam. These next two questions are both similar in concept. They're from different sections. They're actually from different chapters, but there's a very similar concept. And when we went over the review section in the first week, this was something that I really wanted to drive home at that point. I think I went over it last week too, is that these tables that contain the properties of limits or the properties of logarithms or the properties of exponential functions, these tables and these properties are something that you need to know really well, because you're going to be working with them all the time. And these property tables kind of like, they write the rules for you on how you're going to work with this stuff. So these next two exercises from the exam are just using those properties. So what I'm going to try to do is, for each of these, I'll try to list the property I'm using while I'm using it. So the first one states, suppose that log base b of 2 equals a and log base b of 3 equals c. Use the properties of logarithms to find log base b of 72b. So don't let letters weird you out. They're just, you can think of them as a number you don't know yet. So let's start log base b of 72b. Now I notice that this is, so I'm going to break this apart right away. So this is 72 times b, which is, so don't forget my log base b. This is 8 times 9 times b. So how am I going to write that? Let's write that like this. So this is where, so I haven't done anything yet, right? I've just rewritten what's inside a little bit different. This is where I do my first rule. So this can be written as, now I used it twice here. So here, this is the rule that log base x of AB is equal to log base x of A plus log base x of B. So that's saying if you have a product inside of the log, you can split it out as a sum. Okay, and I used that 2 times. Now, I'm going to rewrite this as log base b of 8 plus log base b of 9. And then this is 1. Why is this 1? Well, this is another rule. It says log base a of a equals 1. So whenever the base and the number inside the log function are the same, that's the same as just being equal to 1. And then, maybe I can do this in a different color. No, never mind. All right, so there's one other thing I can do, because I still haven't written this in the simplest way that I can. And what I want to do is I want to use this fact here and this fact here. So I need to get a 2 and a 3 in here somehow. Well, I noticed that 8 is 2 cubed, and 9 is 3 squared. So again, I didn't use any log properties there. It's just rewriting it. But now I'm going to use the log property where I can bring the exponent out front. So this is 2 log base b 3 plus 1. So this property is log base x of a to the r equals r log base x a. Okay. Lastly, I'm going to use this fact here. So let's call these things here, let's call that star. Okay. So now I know that log base b of 2 is equal to a, so I can write this as 3a. Log base b of 3 is equal to c. I write 2c plus 1. And this is by a star. And I'm done. So there's a few things here, and really it helps to write this stuff out as you go. It's going to help you remember. It's going to help you remember these rules. This next one is a little bit more straightforward. So they give you two limits. They say the limit as x approaches 4 of the function f of x is 9, and the limit as x approaches 4 of the function g of x is 27. And then it says use the limit rules to find the limit. So this is obviously from a larger bank of problems because we don't have a g of x in our problem. So we only really need to know the limit of f. Now this is pretty quick, because if you go, so this is limit rule 8. I'll write it up over here. I'll just write it in black. This is on, the reason I call it limit rule 8 is because it's 8 on the table on page 140. And it says, for any real number, b greater than 0, the limit as x approaches a of b, the f of x is equal to b to the power of the limit. So basically what that means is we can just pass it's called passing the limit into the exponent. So if we notice this f of x here, that's the same as the f of x here. So if I'm gonna color code these things again, which I like to do, this b is this 2, and use a red. This 4, this a. So now I just kind of plug in the numbers where they need to go. So I have, let's stick to blue. Limit as x approaches 4 to the f of x equals 2 limit x approaches 4 f of x. And from above, right here, you know that this is 2 to the 9th power. If we evaluate that, that's 512. So it's just one property that we use there, just one. That's a good one to know. All right, 3.2, we dealt with limits and continuity. So continuity, if you recall from my last video, I kind of compared continuity to the concept of being able to draw a function without lifting up your pen. So that means it's defined everywhere. It's, there's no holes, there's no jumps, it doesn't blow up to infinity at some point. So this question asks you to figure out where it's discontinuous, and for each value that it is discontinuous, find the limit, if it exists. So first, where is it discontinuous? Well, the things that we usually look for are, square roots. So if there's negatives in the square roots, or if there's things like that. But generally, it's usually only discontinuous wherever there's a 0 in the denominator. So I should say that a function isn't really. So if you have the square root function, it's not discontinuous where it's negative. It just doesn't exist where it's negative. So when we have these discontinuities, we want single points, and that's always going to be 0 in the denominator. So here our 0 is x equals -2. Since x plus 2 is 0, so this says the bottom is 0 when x equals -2. So you see that you take -2 plus 2, you get 0. Okay, so now we need to find the limit. Well, if you notice, so this is actually, if we draw this, I'm going to draw this function quick. Is this an interesting function? So here's -2. So it's undefined here. There's -1. There's 1. So we're undefined at -2. What happens is this function goes like this. And then this. So, because you can see that really this function, it looks kind of like 1, right? It looks like the x plus 2 should just cancel the x plus 2 on the bottom. And that's essentially what's happening, except that there's this absolute value. So when we think about it, so let's say when x is less than -2, so this is also how we kind of do the limit. So let's make a table. So let's do x. Let's do an x p of x table, right? P of x. So let's do. So we know that it's not defined at -2, so we want to approach -2, and let's do it from both sides. So let's do 2 tables. So let's do the left and right hand limit. Because the limit could not exist. Based on this picture, it shouldn't exist, right? Because the left and right hand limits don't agree, but we should see why. Okay, so if I plug in x equals, let's do 3. Let's do 2.1. Let's do 2.001. So x equals 3, I get the absolute value of 5 over 5. Oh, these need to be negative. I'm sorry. So this is me coming in from the left side. So on top I have the absolute value of -3 plus 2, which is -1, so the absolute value of that is 1. And on the bottom I have -3 plus 2, which is -1. So that gives me 1 over -1, which is -1. Again, for -2.1, I have the absolute value of -2.1 plus 2, which is the absolute value of -0.1, which is 0.1, positive 0.1. And on the bottom, I'll have a -0.1 again. So 0.1 over -0.1 is again just -1, because they cancel each other. And I'm going to get something similar for this. Now, approaching from the other direction, let's say I wanted to do -1, -1.9, -1.99. Now, the top will always be positive because there's an absolute value there. But because these negative numbers are smaller than the other number on the bottom, so -1.9 plus 2, the positive 2 is bigger than the negative 1.9, so that number is going to be positive as well. So I'm going to get nothing but 1s here. So this is like, so here's me coming in from the right. I'm getting really close, and then here's me coming in from the left. So this limit, p of x as x goes to negative 2, does not exist, since the right hand and left hand side, right hand, left hand limits don't agree. They exist, but they don't agree. They're not the same. I remember last week I gave a condition for the definition of a limit and when a limit exists. And they have to be that both the right and the left hand side limits exist and are equal. If you like this kind of function, go and look up what's called Heaviside step function. So this is just like for more, if you're interested in this kind of thing. Okay. 3.35. This is a very straightforward problem on rate of change. So this is just going to be another sort of plug in a formula kind of thing. The other exercise from this section is a bit more interesting and a bit more difficult, but it was something I did in last week's video. So if you want to see that, I suggest you go watch last week's video. That's week 2. It's problem 3.317. You can go look it up in the timestamps and watch a video of it. It's on instantaneous rate of change. Okay, so for the average rate of change, we have a formula. It's just like the slope. It's rise over run. So let's put that over here. Average rate of change is given by this formula. F of B minus F of A over B minus A on the interval A from A to B. So here our A is 1 and our B is 4. So this is the interval. Let's highlight all of these. So, and then our function, so our f, if you will, is the square root of x. So all we do is say, well, we want the function evaluated at b, so that's square root is the function, and b is 4, so let's actually write that. So this is b, this is a, and this is f of x. So f of 4 minus f of 1 over 4 minus 1 equals the square root of 4 minus the square root of 1 over 4 minus 1. This on the bottom is just 3. And here we have 2 minus 1. So that gives us 1 on top, 3 on the bottom. That's all it is. I should circle this too. Okay, 2 left. So this one's probably the longest problem. It just has a couple parts to it. But the one after this is probably going to be most indicative of what you're going to see in the future and probably what you're looking at now. So 3.4.21, it's a 2-parter. It says find the equation of the secant line through the points where x has the given values, and b, the equation of the tangent line when x has the first value. So in order to find the secant line through the points, now remember this is just, so if we want the secant line, let's see if I remember how to draw this. Yeah, so it should just have, so this should look something like, I think it's something like this, maybe. Doesn't really matter that much. So let's say here's 3, here's 5, here's that point, here's this point. So secant line is just the line that connects these 2 points right here. So let's do this in a different color. No one's going to see that. Here's the secant line. Okay, this is a bad example. Let's just let's redraw this. So I want to zoom in on this a little bit better so that you get a better idea. So let's just pretend you have this going on. 5 is over here somewhere. One day I'll get this right. Okay. Let's do something like that. Okay, finally, I drew the thing. So a secant line is a line like this that connects 2 points. So this is the secant line. And a tangent line is a line tangent to a point. So let's say right here, it's the line that just touches the curve once. Right there. So right there. There's the tangent line to x equals 3. So these are the lines we're interested in. So let's do part A. So usually a good thing to do, if we can do it, is to find the slope of the line first. So we need the slope of the secant line. So we're going to do rate of change, or the slope formula. Now we have 2 points. Let's figure out, so we have 3 and f of 3, and 5 and f of 5 as 2 points. So let's just figure out what f of 3 is, and f of 5 is, so we can use those points from now on. So if we stick 3 in for that function, we have 3 squared plus 2 times 3, which is 15. We plug in 5, we have 5 squared plus 2 times 5, which is 35. Okay, so with our rise over run formula, our rate of change formula, we do f of 5 minus f of 3 over 5 minus 3. This is 35 minus 15 over 5 minus 3. We have 2 there, 20 there, and that becomes 10. So 20 divided by 2 is 10. All right, so this is the slope of the secant line. Now we're just going to use one of those points that we found out earlier, and the slope, write it in point slope form, and then we'll be good to go. We'll have our equation. So our new point, after we did some math, this should be 315, and this should be 335. So that's just coming from this right here. Okay, so in point slope form, we do y minus the y value, so that's 15. I'm going to pick the first point here. It doesn't matter which point you pick. This is equal to the slope times x minus the x value, which is 3. I'm going to add over 15. So y equals 10x minus 30 plus 15. And then simplify. Y equals 10x minus 15. So this is the equation for the secant line. So we're done with the first part. Now the second part asks us to find the equation of the tangent line when x has the first value. So when x equals 3. So how we do that is we find the instantaneous rate of change at x equals 3. Because that gives us the slope at a specific point. And then we can use the information that we just got from the previous problem and figure out the rest of the previous part. So we need to find limit as x approaches 3 of f of x, excuse me, it's not of x as x approaches 3, is the limit as h approaches 0 of f of x plus h minus f of x over h. So this is going to be equal to limit as h approaches 0. Now we plug stuff in. F of x is x squared plus 2x. So we're going to plug in x plus h everywhere there was an x in that function. And then f of x normally. This is all over h. Move it down here. So now we're going to kind of FOIL stuff out and distribute a negative and just kind of simplify everything on top. So x plus h squared, this is x squared plus 2xh plus h squared. I do these pretty quickly. There's a formula for this if you want to remember it. If not, just do the foiling out and you'll see that it works out. 2 times x plus h is 2x plus 2h. Now I'm going to distribute this minus sign, minus x squared minus 2x. This is all over h, and I can't forget my limit. So I'll make room for it. And then I'm going to start canceling stuff. That's what this lovely red is for. All right, so 2x, positive 2x, negative 2x. Negative x squared, positive x squared. Okay. Now remember, if I did this math right, there should be an h term and everything on top, because that allows me to divide. If I don't have an h term, everything on top, chances are I did something wrong or the limit doesn't exist. But I do. So I can cancel those as well. So I cancel 1h from everything up top, and it allows me to cancel the h on the bottom. And then this gives me limit as h goes to 0 of 2x plus h plus 2. Evaluating this limit, I plug in h for 0. It's equal to 2x plus 2. And now remember, I'm curious, I want the tangent line or the slope at x equals 3. So now I'm going to plug in x equals 3. Okay, so this is the slope of the tangent line. So the secant line, we find the slope by finding the average rate of change between 2 points, and the slope of the tangent line we find by finding the instantaneous rate of change at 1 point. Now all that's left over is to again use the point slope form with one of the previous points we have to figure this out. Now, with a secant line, I could have picked either of these 2 points and it would have been fine. So this one or this one. But notice only the red arrow, only this dot is on the tangent line. So I have to use that point. If I knew another point on the tangent line, I could do that, but right now I don't. So I have to use the first point. So again, we do point slope form. It's going to be the same things here, the same y and x. So y minus 15, but our slope is different now. So there's an 8 here instead. And then it's x minus 3. This gives me y equals 8x minus 24. So that's the distribution. And then I'm adding 15 to the other side. And then this simplifies to y equals 8x minus 9. And this is equation of the tangent line. Okay. So we're done there. That's it for that problem. That had a little bit more moving parts to it, but hopefully you found it okay. But if you didn't, that's why we're doing them, right? Okay, so this is the first section of chapter 4, which is about derivatives. And derivatives, think about the derivative as an instantaneous rate of change. It's defined with the same limit definition as we did when we were, or as we used when we were talking about instantaneous rate of change. But now we get to do a little bit more with it. We get a few nice rules for finding derivatives, so you don't have to do all of this limit stuff over and over again. So one of the rules that we get, and we're going to use them both in this one actually, so 2 of the rules. We have the power rule. These are very important. So remember we talk about the derivative of f. We use the notation for that as f prime of x. That's what that apostrophe is there. So maybe I'll just write that up here, because that's not what I want to write. So the power rule says that if I have some x to the n power and I take its derivative, then all I have to do is bring the n out in front as a multiplication or a product, and then lower the power by exactly 1. And then I have the sum difference rule. And this is, basically it says that I take the derivative of 2 functions, f of x plus g of x. It's the same as taking the derivative of each of them separately and then adding them. And then the same goes for taking a difference. So if you look at the problem here, it says find the derivative of the function f of x equals 6x to the 3.5 power minus 10x to the 0.5 power. You can see that we're going to use both of these rules. So let's just call this 1. Let's call this 2. So we have derivative 6x 3.5 minus 10x 0.5. This is going to be equal to, now I'm going to use rule 2. It's going to be equal to the derivative of the first thing minus 10. Oh man, I forgot a rule. So there's another rule that I'll talk about right after this. So I'm going to need it. So actually, let's do it right now. So let's do number 3. I'm just going to call this the constant rule. So what it means is I have the derivative of a times some function where a is a constant. It's the same as pulling the a out and then doing the derivative. I'm going to need this. Okay, so this was rule 2. Let's put that here. Then this direction. So now what I'm going to do is I'm going to pull this 6 out. I'm going to pull this 10 out using that rule that I so eloquently forgot. So that's 3. And now I can use rule number 1. Don't need this anymore. So rule number 1 says pull out the 3.5 and I lower by 1. And then pull out the 0.5, lower by 1. Now I'm just going to simplify. So 6 times 3.5 is 21. Ten times 1/2 is 5. And I'm done. All right, so I imagine you're doing a lot more with derivatives right now, but if you wanted to figure out a little bit more of what went wrong on the exam, if something went wrong, hopefully this helped you out. Remember, my office hours are all the time. Send me an email. So I look forward to hopefully seeing from some of you. Otherwise, I'll make another video next week. Bye, everybody.